Class key in your headers. Let's just give another minute, another 1 minute for your friends to join. Today we'll be starting a new topic. So the electromagnetic induction, as usual, the word notes at the back got questions with answers. Try out the questions and check the answer. Then pass your paper, pass your questions, the topical in times. Okay, do that. Then after that, go to the extreme. The exam mate, right? So you can get more topical questions. So try to familiarize with the questions. Okay, so let's start. So we'll be moving on to the next topic, alternating current. Okay, we'll be starting with alternating current. Okay, so alternating current is quite close link with the magnetism actually. Why? Because of transformer. Okay, actually transformer links magnet with alternating current, right? Transformer works based on magnet, electromagnet, and transformer only can use alternating current. So that's why the topical question you check from the times is also the induction and alternating current together. Okay, sometimes the question will be together. Okay, so let's see, go on. So AC in your AS you learn DC, direct current. Direct current. In A2 you're going to learn alternating current. Okay, so which is better? Of course, alternating current as an advantage, right? That's an advantage. Okay, let's discuss that. What is the advantage? Okay, these are the three subtopics we're going to learn. First, we're going to talk about the characteristic of alternating current, the features of alternating current, how the transmission of electrical energy is applied to household. The part 2, I think indirectly you learned earlier. Step up transformer, step down transformer. We will recall back in 11.2. And third, we discuss about rectification. Rectification is a technical name of the process changing DC to AC. AC to DC. Alternating current to direct current. The process of changing AC to DC is called rectification. Okay, by using a diode. This is also a short topic. Okay. Okay. So when it comes to current, AC DC is actually, we can't forget these two inventors. So of course, Thomas Edison and Nikola Tesla. So both are pioneers who promote current, but both of them have some difference, right? Edison actually promoted DC. Edison promoted DC to be supplied around the world, okay, to supply the electrical energy. But Nikola Tesla promoted AC. He said AC is better way of transmitting the electrical energy to the surrounding. Okay. So yeah, now you know. So who's the winner finally? Eventually, the Tesla, AC power that won the battle. Okay. So yeah, so Tesla. Until now, you can see your houses. What type of current has been transmitted by the TNB to you? Alternating current, right? AC. Okay, why AC better than DC? Why AC better than DC? Because AC, the voltage can be altered by using transformer. Okay, the voltage of AC can be altered by using transformer. That's the main advantage. Okay, the main advantage. To go in depth is because of why alternating current. Another reason is because its voltage can be easily step up and step down, as I told you, by using transformer. Okay, why the voltage need to be step up and step down? You learned this in your O levels, right? Why the voltage need to be step up and step down? Okay, for that we go to the next slide first. We come back to this slide, this picture first. Okay, so you know, power plant. There is a power plant generating electrical energy, and the at a certain voltage. Okay, and the current is transmitted through cable for a few kilometers away to your houses. Okay, so now of course, what voltage to be used in the cable? Okay, I believe you learn in your early studies, right? High voltage or low voltage need to be used in the cable? High voltage, right? The cable must use, the current need to be transmitted high voltage. Okay, why the current need to be transmitted high voltage in the cable? Okay, why? So the reason you learn, right? We go back to the earlier slide. The answer is there, right? This is the answer. Okay. Why high voltage power is transmitted? It reduces. Why? Because if you supply the electrical energy through cable with high voltage, the energy loss transmitted to the cable is reduced. Okay. Energy loss transmitted to the cable is reduced. The heat loss in the cable is based on I squared R. Okay. The I is the current flow in the cable. The R is the resistance of the cable. Okay. So the heat loss in the cable can be reduced by decreasing the current flow. Okay. Okay. For a better description, let me go to the whiteboard. Explain to you. Okay. Let's say this is the power station. Okay. The power station. Okay. It's connected through a cable. Then to the houses. Okay. Okay. So you can imagine that the power about the station has its own power. It has its own power. Okay, you know, like a Bakun dam, the different hydroelectric dam. They will tell you, well, what is the power of that station. So the power of the station is fixed. Okay, so it has a fixed power. It's constant. Okay, so P equals to IV. P equals to IV. Okay, the voltage of the power station can be increased. You can increase the voltage of the power station by using a transformer. You can use a transformer. Okay, use a transformer, step up transformer. Step up transformer used to rise the voltage. Okay, why the voltage need to be raised? Because the power station has a constant power. If it uses high voltage, if the voltage produced by the power station is very high, based on P equals to IV, the current flow in the circuit will be reduced tremendously. Okay, the current flow in the circuit will be reduced tremendously. Based on what? P equals to IV. When V is very high, the current will be very low. but the power is constant. The power of the station is constant. Okay. So when the current in the cable is low, when the current flows in the cable, power will be lost in the cable. The power loss in the cable, we use I squared R. The current flow in the cable squared multiplied by the resistance of the cable. This is the resistance of the cable. Yeah, so we know whatever power generated by the power station, do you want to be used by the cable as a heat, or you want to transfer it to the houses? Of course, you want to transfer it to the houses, right? The power, not wasted in the cable, correct? So we want to limit the power loss in the cable. So how we can do that? By decreasing the current flow in the cable. Okay. How we can decrease the current flow? By using a step-up transformer by raising the voltage from the power supply. We raise the voltage of the power supply by using a step-up transformer. Therefore, power of the power supply is constant. Power station is constant. So current will be small. Okay. Yeah. So this is how power loss minimized. You know, if power loss is low means the efficiency is high. More power will be channeled to the houses. Okay. So this one Tesla idea is works. So if the power station is a AC alternating current, the voltage can be altered by using a transformer. Okay. Therefore, AC is the winner. Okay. AC has been selected and is most suitable to be transmitted around the world to households. Okay. So hope you got the idea. Okay. So we go back. So this is the reason. This slide tells the reason. I hope you can understand. So why high voltage is used? Because heat loss is I squared R in the cable. So power produced in the plant is P equals to IB. P is constant, constant for the power plant. So if you raise the voltage, the current in the cable will drop. So power loss can be reduced. So conclusion is, if V is made big, Q heat loss will be small. Okay. So AC is the winner. AC. DC problem is, of course, transformer can't work based on DC. Okay, you know that why. We learned the previous topic, right? Why transformer can't use DC? Why transformer can't use DC? Because if DC supplied to the primary coil, the core, iron core, can't produce changing magnetic field strength. Okay, therefore no changes in flux will experienced by the secondary coil. Therefore, no EMF will be induced. So the story you know, so DC can't work on transformer. Okay, that's one reason. So this is why alternating current is selected. Okay, so to minimize the energy loss in the cable, voltage need to be increased. So voltage only can be increased by transformer, and transformer only works based on AC. So that's why AC is selected. Okay. Okay, in past year, suddenly question comes out. Give one advantage, one disadvantage of alternating current. Okay, one advantage, one disadvantage. We only know advantage, right? Advantage because this transmission, this story, can be used by transformer. Voltage can be raised so that energy lost, power loss in the cable can be reduced. What is the disadvantage of AC? Anybody? One disadvantage of AC? The disadvantage of AC is the circuit little complex. Okay, the circuit is complex compared to circuit for DC. Okay, that's the disadvantage. Lots of components required to generate alternating current. Okay, so that's disadvantage. Please include your notes. The disadvantage of alternating current is the circuit for alternating current is complex. Okay, compared to DC. Okay, guys, any questions so far? Why AC better than DC? Okay, so we got the idea. Okay, so let's go on. Okay, I already told you why. So from the power station to the cable is step up transformer. Then when it comes to cable to the household, step down transformer. You want to charge your phone, the high voltage, few thousand volts in the cable need to drop to 6 volt. Maybe your charger is 6 volt. So we use step up transformer to reduce the voltage. Okay. So as I told you, if you have a laptop, no choice. The laptop, the adapter, the adapter used to step down the transformer. There is a transformer, and the adapter should have a diode to convert AC to DC, because laptop uses DC. Okay. Your phone also uses DC, direct current. Okay. Any devices at the back got battery with a fixed terminal, positive negative terminal. It's DC then. Okay, it's a DC. Okay. Okay. So the winner is AC generator. We use an alternating current generator, not a DC generator. So the coil will turn in a magnetic field. So magnetic flux linkage. The changes in magnetic flux linkage will experienced by the coil. So induces an EMF, and because the closed circuit, current will be flowing out from this circuit. Okay. Okay, so I need to tell you something about magnetic flux and magnetic field strength. We are a little going back to the topic, the earlier topic, induction. Okay. What I want to bring down now is about this diagram. Okay. Okay. This is the alternating current pattern produced by the generator. Okay. Okay, now you see the coil in the first diagram here. When the coil is vertical, okay. How about the flux? Flux graph. Okay, so flux versus time. Okay. When the first diagram, the coil is vertical. The coil is like vertical. Vertical. The magnetic field is exposed to the coil. Okay. The flux is maximum or minimum? What is flux? Flux linkage B dot A dot N, right? So when the coil is vertical, the flux is maximum or zero? Flux is maximum, right? Because the magnetic field is 90 degrees, the area times the B will give you the flux. Okay. So when the coil is vertical, the flux will be maximum. Okay, will be maximum. Okay, the first diagram, first picture. When the coil rotate 90 degrees, you see the second picture. When the coil rotate 90 degrees, the coil become flat. Flat. The magnetic field just moving up and down. So the magnetic field is parallel to the surface area. The magnetic field is just parallel to the surface area. So the flux drop to what? Drop to zero. For the second picture. So this is how it's going to become, how the flux change. Flux is maximum when the coil is vertical. That's the point I like to highlight here. When the coil is vertical, the surface area is perpendicular to the magnetic field. The flux is maximum. Okay, correct? You see the diagram here. But this graph is EMF. This graph is the EMF induced. Okay, so you see, flux is maximum. But when the coil is vertical, flux maximum. But the EMF generated is how much? EMF generated is zero. Okay. The flux is maximum, but EMF generated is zero. Okay. So this is the point I like to highlight. When the flux is maximum in the AC generator, the EMF will be zero. Okay. When the coil is flat, flat means when the flux is zero, the EMF generated is maximum. Okay, why? Okay, let's go to the next picture. Okay, this is better. Okay, this diagram shows better. You see the first diagram on top. This case, the coil is vertical, right? So you see the first this vertical, the coil is vertical. The flux is maximum, but EMF induced is 0. EMF induced is 0. You know, right? EMF is what? According to Faraday, is negative rate of changes of magnetic flux, right? Magnetic flux linkage, magnetic flux linkage. Okay. Sometimes they put the N outside here, N outside here, negative N d psi over dt. Okay. EMF is the rate of changes of magnetic flux linkage. So you see the diagram of flux. The flux, what shape, what graph is that? It's a cos, right? It's a cos graph, cosine graph. So flux is cosine graph. EMF going to be what graph? So you differentiate the flux, right? So cos you differentiate, you get what? Cos you differentiate, you got negative sign. Cos you differentiate, you got negative sign. Then you got negative here, so it become sine. So the EMF become sine. So remember, if flux is maximum, EMF will be 0. When flux is 0, EMF will be maximum because of this differentiation. Okay, so important, guys. So remember, when the coil is vertical, flux is maximum, EMF 0. Okay. Yeah. So this is recalling back the graph of flux and the EMF, right? The last lesson we did. Whatever flux graph I give you, you should know how to come out with the EMF graph. But here, what is the new highlight is when the coil is vertical, flux is maximum, EMF is 0. Okay, any questions from this diagram? Okay, so hope you got the idea. Okay. Okay, so let's move on about alternating current. Okay. Okay, so AC, alternating current. Okay, alternating current is actually produced by an oscillator. Kind of electron is allowed to oscillate back and forth, create alternating current. It repeats itself in a fixed interval. This 4 diagram here is all of them are alternating current. Okay, but in your syllabus, the most of the time they'll ask is the first one, the sinusoidal alternating current. Okay, how do you know it's alternating? Because positive and negative. Positive means the current flow may be clockwise. Negative means the current flow in anti-clockwise. Okay. The second one also alternating current, positive, negative. This is called square wave. It's called square wave AC, alternating current. Yeah, square wave. Okay. And you got many types. As long as positive and negative is there, it's alternating current. Okay. Remember, if the current is sine, then the voltage which produces this current also sine. Remember, when the voltage is sine, current also will be sine. Voltage cos, current also will be cos. Of course, right? V equals to IR. When voltage rises, current rises, right? Yeah. So their graph pattern going to be the same. V and I always will have the same pattern of graph. Okay. Okay. Now go. So the first diagram on the left is a DC, direct current source, battery. Your DC supply, right? DC, this is DC. Positive terminal, negative terminal is fixed. The current flows in, the electron flows in one direction. Of course, current flows in one direction. The alternating current, this is the symbol. Like sine wave symbol. The current flow, half cycle flow clockwise, another half cycle will flow in anti-clockwise. Okay, alternating current. Okay. So in an AC circuit, the electron drift to one direction, then reverse drift in the opposite direction. You know that. Unlike in DC circuit, the electron do not move around entire circuit, but simply move back and forth along the wire. Okay, man, there is a mistake. The electron drift to one direction, then reverse drift in opposite direction. Yeah, the AC. DC circuit, the electron do not move around entire circuit. Move back and forth along the wire, just one way DC. Okay, when you purchase a battery, dry cell, okay, the only information needed is what is the voltage of the dry cell, 1.5 volt. Okay, but now if you have alternating current source, power supply with AC, okay, there are lots of information needed. Okay, because it's alternating current like a sine, like a wave, so it will have all the property possessed by the wave. Okay, the oscillation, because it's a periodical oscillation, so it will have a period, it will have a frequency, it will have an angular frequency. Okay, so the TNB keeps us alternating current. Okay, the alternating current supplied by TNB is, I think, around 230 volt, right? Around 230 volt. You heard about that. It should be 230 to 240 volt. Okay, but you never heard of the frequency. Okay, what is the frequency sent by TNB to us? Roughly around 50 hertz. Okay, the frequency of the AC supplied TNB to us is like 50 hertz. Okay, means what? Yeah, of course, 50 times, 50 oscillations in a second. 50 times the current will back and will change the direction of flow in a second. Okay, that's frequency. Okay. So in exam, the property of alternating current is they can ask what is the period, what is the frequency, what is the angular frequency. Angular frequency, recall back the same formula as angular velocity, but it's angular frequency because of oscillation. So 2 pi over t or 2 pi f can be used to find the angular frequency. Okay. Of course, the unit is what? Radian per second. Angular frequency. Okay. Okay, hope you got the idea. Okay, let's move on. Okay, so I think you're familiar with this equation, right? For a wave also, any sinusoidal graph, right? Mathematically, this is y, this is x. So y equals to x naught, y naught sine theta, right? You write, or is y equals to y naught sine omega t. Y naught is the peak value, correct? Okay, in math you learn, right? Sinusoidal, how the equation for sine graph should look like. So same thing for alternating, because alternating graph is a sine graph. Okay, so the x is the whatever quantity in the up here. Okay, so let's say it's current versus t, AC current. So how the equation going to be look like for the I equals to the peak value. The peak value, normally we put I naught. So I naught sine omega t. Yeah. So this is the formula for alternating current. I naught sine omega t. If it's I. If it's V, then the voltage will be V naught sine omega t. V naught sine omega t. Yeah. So sinusoidal form of simplest form of oscillation. So the AC we will have I equals to I naught sine omega t. We will have V naught sine omega t. Okay. Remember, the V and I, the phase difference is 0. They will have the same shape of graph. If V is sine, I will be sine. If V is cos, I also will be cos. Okay. So of course, the omega you can replace with 2 pi f, right? You can replace with 2 pi f. 2 pi f. Okay, let's say someone said in let's say someone said in industry, the current changes. The formula for AC current is 5 sine 5 50t. Let's say they give formula like this. The alternating current supplied to one instrument is 5 sine 50t. Okay, so from this formula you should be able to find the period, frequency, the peak current, and so on. Same like wave. Okay, so whatever beside the trigger, the 5 will be your, of course, the peak current, 5 ampere, let's say. Okay, how you can find the frequency and period? Of course, whatever beside the t, the sine omega t, right? Of course, beside the t is omega. The 50 is omega in this case. So omega equals to 50. So you know omega is 2 pi f. So you can find the frequency. You can work out the frequency. So remember, whatever number beside the t is your omega. If you know omega, you can find frequency, you can find period. Okay. Any questions? So far you can understand. Okay, so let's be continue. Okay, so alternating current, it has a peak value. Actually, the voltage is varying from up to down, right? You know that. So it has a peak values. So if you channel the alternating current to a CRO, CRO can trace the graph. So of course, from the equilibrium to the top is the peak value, right? I naught and V naught. Okay, so this is the peak value. Or the crest to trough, this is called peak to peak value. Peak to peak value. Actually, peak to peak value is 2 times of the peak value. So peak to peak value divided by 2, you get the peak value. Yeah. Okay. Okay. Now we go a little deep about direct current, alternating current. Alternating current. Okay. Before we go to this slide, okay, I want to tell you one problem. Okay. See, let's say you have a light bulb. The light bulb here stated labeled. You apply 3 volt for this light bulb. Okay. To get so that the light bulb has a normal brightness. Okay. So you go and connect with the, let's say, direct current. You connect with the direct current. Okay. 3 volt. So you get the normal brightness. Okay. So no problem. Okay. Now, let's say you want to light up the same light bulb, but you want to connect with the alternating current. Okay. So the alternating current, of course, must give to make normal brightness for this light bulb. What value must be same as the 3 volt of the direct current? 3 volt of the direct current. Is it the peak value of 3 volt? Is it the peak value, V peak? Is it the peak value of 3 volt can make the light bulb to light up the same brightness as the 3 volt of the direct current? Can or cannot? Is it peak value of 3 volt? Can give the same brightness, same level of brightness as the 3 volt of the DC? Can or cannot? Come on, anybody? Can or not? Because the direct current voltage versus time, how the graph looks like. If 3 volt means it's going to be constant 3 volt, right? It's going to be constant 3 volt DC. But AC, if peak is 3 volt means the graph is changing like this. The voltage of the AC is changing like this, up and down. But the peak is 3 volt. Is this can give the same brightness at the brightness of the 3 volt of the DC? Anyone? Okay. Jantat, yeah? Jantat, what do you think?
I'm not sure.
So, but to get the 3 volt, yeah, peak voltage, 3 volt only happens at only a certain time only. No? After that, the voltage drop to less than 3 volt, right? So is it going to be normal brightness? Not really. No way. So the peak voltage of 3 volt not equivalent to the voltage of the DC, which is going to give the same brightness. Okay. Then what value? What value of AC? What value of AC can give the same brightness as the DC 3 volt? What value? What is the name of that value? Definitely not peak. Then which value? So that's what we're going to discover. Which value of the AC which will give the same brightness as the DC voltage. Okay. So to explain that, this slide tells that information. Okay. So look at this slide. So on the left, okay, on the left is a direct current, is a resistance R. Okay. Let's say the power dissipated by this direct current is I squared R. I squared R. I, we know I for the direct current is constant, right? I versus T. I is constant. So I squared R is the power dissipated in this resistance, right? Okay. Now come to AC, something new. Okay. We can't say power. We put as average power. This sign, this bracket is average power. It's average power. Because actually the alternating current, the power is changing. The power is changing. Big voltage means power grade. Okay. Okay. Sorry. Excuse me. Yeah. So when the voltage is very high means the power is high. When the voltage drop means power drops. So to get for the AC, we write average power. The average power of the AC must be same as the power dissipated by the direct current. That's why I put this sign. Is equals to I squared R, but I also changing. Okay. I also changing. So because if V is sinusoidal, I also sinusoidal. So here we put average current, like a bracket. So I squared average current. Yeah. So what we are trying to do, we want to find the value that equivalent to the direct current. So to get same brightness, let's say the resistance is a light bulb, so same brightness, these two power have to be the same. Okay, the average power produced by the AC must be same as the power generated by the TC. Okay, yeah. To obtain the effective value for current that can be calculated easily, we compare the heating effect of the alternating current and the direct current. If power generated by DC is same as the mean power generated by the AC, so mathematically you see PDC, PAC should, if it's same, so I squared R is same as this called mean square speed. This is called mean square speed. Mean square speed. Okay. Yeah. So I squared R must be equals to mean square speed. Mean square current. Mean square current multiplied by the R. So the IDC, you make the IDC as the subject. So yeah, you get, now you know what value the direct current, what value is equivalent to the direct current, which give the same power dissipation. What is the name of this current? Is root, you see, got root, is called root mean square value. This is called root mean square value. Okay, see, root mean square value. So I go back to the diagram, go back to the initial diagram. Okay, the whiteboard. So I just want to ask, yeah, which value going to give the same brightness? That means same power dissipation, as the direct DC voltage. The value here is not peak, of course, but it's the RMS value. It's called RMS value. The RMS voltage should be equivalent to the DC voltage, which can give the same power dissipation. Okay, so RMS value, we call it RMS value. How do you know it's RMS value? Give the equal to the direct current value, gives the same power. So just now we derive it. P same as the PAC. So if one IDC is equivalent to RMS value of the alternating current. Okay. So the famous definition for alternating current. Okay. In exam they will ask, what is meant by root mean square value? What is meant by root mean square value? It's a 2 marks question. Define. What is meant by root mean square value of alternating current? We define the root mean square of a current IRMS as the steady current, equivalent to a steady current that would convert electrical energy to other form of energy in a given resistance at the same rate as the alternating current. So that is RMS value. Okay. So what is RMS value? RMS value is a value of alternating current which equivalent to a direct current, which dissipate the same rate of heat. Rate of heat means actually power, which dissipate the same rate of heat across a resistor. That is RMS value. Okay, first time you come across this. Okay, so to be easier, okay, let me go to the Word file. You can see the definition quite clearly. Yeah, is the alternating current, the nodes. Okay, yeah. So this is your definition of root mean square. Okay, come on, worth recalling back. So what is root mean square value? A root mean square value of AC is defined as the equivalent value of steady DC, 1 mark, DC, which would dissipate heat at same average rate. Or in other words, this heat at same average rate is actually power. You can say which would dissipate same power as the AC in a given resistance. That is root mean square value. Okay. Guys, very important. The highlight of alternating current is root mean square value, RMS value. Okay. RMS value of AC is a value that equivalent to a DC, which dissipate the same rate of heat across a resistor. Okay. Okay. So yeah. So how they got this? I think now I go back to the early slide. Makes sense, right? Okay. The RMS value of alternating current is a value that equivalent to the direct current, which dissipate the same rate of heat across a fixed resistor. Okay. Okay. So now because you are in A levels, A levels. Okay. Now they said, okay, you have a battery. You want to light up a light bulb with you want to supply 3 volt of DC. You want to apply 3 volt of DC. Okay. If you have an alternating source, so how much 3 volt you need to apply? The VRMS, the RMS voltage of this AC must be 3 volt. It will give the same brightness as the 3 volt of DC. Okay. Yeah. So this is RMS value. Okay. Any questions? Okay. So now for sinusoidal, okay, only for sinusoidal graph, a current is changing sinusoidally, current changing sinusoidally, okay, the RMS current is linked to peak current by using these two formula. Yeah. So please memorize these two formula. These are the formulas linking RMS to peak value. So IRMS is found to be I naught over root 2. Okay. VRMS is found to be V naught over root 2. Okay. V naught over root 2. But these two formula only works for what? Only for sinusoidal. Okay. Only sinusoidal alternating current. Okay. So, yeah. basically this. So if the current is sinusoidal, then the peak current, right? The peak current is over √2 is your RMS current. Okay, that means, let's say you have alternating current, alternating power supply which has a peak voltage of 8 volt. Let's say it has 8 volt. That means peak here is 8 volt. Okay, that means its RMS value is what? The VRMS is what? VRMS is 8 divided by √2. Okay, 8 divided by √2. Okay, so 8 divided by √2. Anybody? What's the answer you got? 8 divided by √2. Okay, come on. 8 divided by √2. So let's say I just give a number lah. Let's say you got 6 something lah. Let's say you got 6. Let's say 6. So what you should understand that this alternating current is equivalent to a direct current of 6 volt. This alternating current source, this source is actually equivalent to a direct current of 6 volt. Okay, the strength, the energy can dissipate. Okay, so this is the ideal RMS. Okay, so let's go back. This is a mathematical derivation proving that. I'll come back to this. You don't need to know this actually. Extra information. Okay. Yeah. Come on. Just how do you do this question? So this is an alternating current. Can you please find the period, frequency, angular frequency, peak value, peak to peak for this current? Okay, 2 minutes for you. Come on. Find the period, frequency, angular frequency, peak value, peak to peak value of this alternating current. Two minutes. Try to take a piece of paper, try to calculate. Okay, so hope you are halfway of doing the question. Another 1 minute. So period is easy, right? It's 2 milliseconds, right? So yeah, period is 2 milliseconds. Frequency is 1/2. Angular frequency, right? 2 pi over t, right? 2 pi over t can give you angular frequency. Just change the period to second. Peak value, of course, 3 volt, right? 3 amperes. Sorry, this current graph. 3 amperes. The peak, peak to peak, of course, is 6, right? 6. Right. So this is the answer you got, right? Remember the technique. Hope in your mind this is the idea. Straightforward. Okay. So this is the property of alternating current. They will give you like alternating current. They will ask this all the property. Okay. But now, can you please add another one question here? Can you find RMS value for this alternating current? So RMS value is what? RMS value is I peak. Okay, I peak over the √2. This sinusoidal. Yeah. So 3 over √2 will give you the IRMS. Root means square value. Okay. 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 So Last question. Okay, look at this, another example. So this is another sinusoidal wave, alternating current, sorry, it's alternating current. Peak current was 6 ampere. So find the root mean square value of this current. So yes, of course, 6 over root 2. So 4.2 ampere. That means I can say this alternating current is equivalent to a direct current of 4.2, which can generate a 4.2 ampere of current flow. 4.2 ampere, equivalent to a direct current, which can produce a 4.2 ampere of current. Okay. Okay, so another one thing you need to remember, if you give a direct current of 4.2 ampere flow to the light bulb, so for direct current, 4.2 means the entire duration, the current will be 4.2, never fluctuate, fixed 4.2. But if you use a alternating current, okay, you're going to use to get the same brightness for the light bulb, you need to give a RMS value of 4.2. That means imagine you put an alternating current source to the same light bulb. To get the normal brightness, the RMS value should be 4.2. But remember, the current is actually fluctuating up and down. The average is like 4.2 lah. Sometimes the current can go a little higher than 4.2. It can go up to 6. Can go up to 6. The current can go up to 6. But the average power dissipation is the same as the DC power supply. The average power dissipation. Okay. So put it in your mind, if you have a alternating power source and the RMS value, let's say the RMS voltage, let's say the voltage RMS is 6 volt, you should understand that the voltage going to be supplied to by this power supply, the average is like 6 volt, but the voltage can go slightly more than 6 volt because the peak is greater than the RMS. So the voltage can go slightly over than the 6 volt, but actually not really damaging the instrument lah. Slightly higher, that's all. Yeah. Okay, so that's all for today. I don't want to continue. So what you learned today? So you learn about why AC better than DC. Okay, because of energy loss in the cable can be reduced. Okay, then we talk about something called the RMS value. Okay, what is RMS value? A value that RMS value of alternating current is a value that equivalent to the direct current, which dissipate the same rate of heat energy across a fixed resistor. Okay, across a fixed resistor. Okay, any questions? So tomorrow we will proceed. So go back and try to watch the video again and read the notes. Prepare for next lesson. Will be continuing. Okay. Okay. So thanks.
Thanks, sir.
Thanks. Yeah.